Perturbation theory is an approach to describe a complicated system in terms of a simpler one. The idea is to start with a simple system for which a mathematical solution is known, and add an additional complicating factor. If the disturbance is not too large, the complicated system can therefore be studied based on knowledge of the simpler one. In effect, it is describing a complicated unsolved system using a simple solvable system. Let's take one of the biggest unsolved mysteries in physics: Baryon asymmetry. Why is there far more matter than antimatter in the observable universe? The non-dark matter universe is made chiefly of matter rather than consisting of equal parts of matter and antimatter as might be expected. During the extreme conditions of the first few seconds after the Big Bang, a slightly larger amount, about 1/billionth of the total, of regular matter, quarks, and leptons were left over following the creation of matter and antimatter from colliding photons of light, and their subsequent annihilation with each other to reform photons and other bosons. After most of the matter and antimatter was annihilated, what remained was all the baryonic matter in the current universe, along with a much greater number of bosons. It can be demonstrated that to create an imbalance in matter and antimatter from an initial condition of balance, neutral particles such as kaons and mesons oscillate into their antiparticle, also a neutral particle. Their subsequent decays into pions, and interference between other particles leads to slightly unequal amounts of matter versus antimatter. This is referred to as CP violation. So why is there an imbalance? I would reason it is because it is more likely. Think about it this way: to create a universe with exactly 50% of matter and 50% of antimatter, matter and antimatter would need to be created in equal amounts from collisions of photons of light, which appears to be the case. But then, as the particles combine and form composite particles, such as mesons, then oscillate back and forth between their antiparticles and decay at slightly different rates than the particles in their vicinity, and interact with each other, they would need to retain a pure quantum state, rather than a mixed quantum state. A quantum state or eigenstate is a mathematical entity that provides probability distribution for the outcomes of each possible measurement on a system. A pure quantum state implies that we have the exact information about the quantum system. On the scale and size of the universe, even a baby universe, maintaining a pure quantum state with equal numbers of matter and antimatter becomes increasingly improbable as the universe grows in size, resulting in an imbalance, Baryon asymmetry, and therefore a universe with all this matter. There is a required 1 excess quark left over from the decays of neutral mesons per billion antiquarks in the early universe in order to provide all the observed matter in the universe. 1 in a billion is unlikely odds, but the universe is vast and unlikely events happen all the time. In effect, on a large enough scale, the improbable becomes probable.